We've all been there. You're sitting at a red light. It feels like it's been an eternity. You look at the cross street, it's completely empty, and you're stuck,
Yeah.
wondering who on earth programmed this thing. That exact feeling, that universal frustration, is what we're tackling today. We are looking at a really fascinating piece of research that aims to make traffic control smarter, faster, and honestly, a lot more like a human.
Yeah, we're diving into a paper called LLMLight, Large Language Models as Traffic Signal Control Agents.
Huh.
And the mission for you listening is to really get how the reasoning power of these large language models, LLMs, can be used to fix actual gridlock. And maybe more importantly, why this new way of doing things just blows traditional AI out of the water.
Okay, let's get into it. And I think the right place to start is why? I mean, why did traffic control even need a brain transplant in the first place?
Well, the problem is that congestion is just getting worse, right?
Yeah.
Cities are growing, and the solutions we have, they've all kind of hit a brick wall.
So let's talk about those old solutions. There were two main types, if I remember correctly. Where did they actually go wrong?
Exactly. Two main camps. First, you have the older transportation engineering methods. So think fixed time signals or maybe something like max pressure. Their biggest problem is they're just too rigid, they're manually designed, and they just can't adapt to how complex and dynamic a real city is. Then you have the more modern approach, which is reinforcement learning, or RL, systems like CoLight. And these were powerful, they could learn, but they came with these two massive drawbacks that made city planners really nervous.
Okay, so flaw number one, what was it?
It's all about generalization, or really a lack of it. These RL models, they struggle to take what they've learned and apply it to a new, bigger road network. Or what happens when you get something totally unexpected, like a concert lets out and suddenly traffic is 4 times higher. The models they break down. They don't have the common sense for it.
That makes a ton of sense. I mean, if it's only ever seen normal traffic, it's going to panic when it sees a crisis. But that second flaw you mentioned, the black box problem, that sounds like the real deal breaker, doesn't it?
Oh, absolutely. It's the lack of interpretability.
Hmm.
So the RL light makes a weird choice, right? It gives a green to an empty street while everyone else is backed up. And when someone asks why, the answer is, well, there is no answer. It's just a black box. You can't deploy a system that you can't explain to the public.
Right. So the motivation is clear. We need something that can think like an experienced traffic controller, using common sense, but execute with the speed of a machine. And that's where LLMs come in.
That is the big idea behind the LLM-Light framework.
Oh.
You use a large language model as the actual decision maker for the traffic signal. And that's a genuinely new approach.
I love this part. So the LLM is managing an intersection. It needs data, but the data is just numbers, right? Like number of cars in a lane. How does it even understand that?
This is the really clever step. The system verbalizes the data. It turns the numbers into plain English. So instead of just 25, it becomes lane north straight has 25 queuing vehicles. And that text, that observation, gets combined with a task description and, critically, some common sense rules.
Oh, what kind of common sense are we talking about?
Simple stuff, really. Things a human would just know. Like prioritize the lanes with the longest queues, or maybe don't pay as much attention to cars that are still really far away. It's these basic intuitions that the old RL models just completely missed. And this is how you get transparency. Because the LLM uses what's called chain of thought reasoning. It literally thinks step by step in English.
Okay, so a two-step process. The first is the reasoning part, where it looks at all the data and the rules and says, okay, it looks like there are way more cars going north-south than east-west.
Precisely. And then step 2 is action execution. Based only on that reasoning, it decides, okay, I'm going to choose the signal phase that lets the north-south traffic flow. And because it did step 1, it can tell you exactly why it made that choice. Suddenly, the black box is gone. It's a glass box.
This brings up a huge question, though. If you want human-like reasoning, why not just plug in GPT-4 or, any of these massive off-the-shelf models? Why build a whole new one?
That is the million-dollar question, and it's all about domain knowledge. These general-purpose LLMs, they're amazing, but they often lack deep, specific expertise. And worse, they can hallucinate. They can make up facts or logic that sounds plausible but is completely wrong for a specialized field like this.
Wait, what do you mean? Like, it would just make a bad decision?
Catastrophically bad one. In their tests, ChatGPT actually came up with a rationale that said the best strategy was to release the lanes with the fewest cars. It was trying to be logical, but its logic was just backwards for traffic flow.
So it's like a doctor deciding to treat the healthiest person in the waiting room first.
Exactly. And that's why they had to build LightGPT. It's a specialized model. tailored for traffic signal control that's built using this really smart three-stage fine-tuning process.
Okay, this three-stage process feels like the core technical contribution here. Let's walk through it. How did they actually build this specialized brain?
So stage one is trajectory collection and filtering. They basically start with GPT-4 as a kind of super tutor to generate a bunch of decisions and the reasoning behind them in a simulation. But, and this is key, they don't just trust it blindly. They use a pre-trained critic model.
Okay, a critic model. That sounds like a quality control manager on an assembly line.
Perfect analogy. That's exactly what it is. The critic filters all the decisions from GPT-4, and it only keeps the ones where the action led to the best long-term outcome, like minimizing future traffic jams. So the data like GPT learns from is basically a greatest hits of expert-level decisions.
So they're grading the teacher's answers before they even give them to the student.
Yeah.
Smart. Okay, what's stage two?
Stage two is imitation fine-tuning. They take that curated, high-quality data, and they train Light GPT to imitate GPT-4's best moves. This is where it learns the core expertise of traffic management, but in a very efficient way. And then there's the final step, stage three, critic-guided policy refinement. So now Light GPT is smart, but they want to push it to be even better, especially in those weird, unexpected situations. The critic model comes back in, but this time it's not just a grader.
It becomes more of a coach.
Exactly, a coach or a guide. It doesn't give the answer, but it gently nudges Light GPT's reasoning toward actions that will score higher in the long run. This refines its policy without making it too rigid, so it can still generalize to new scenarios.
And the research backs this up, right? I saw that they did an ablation study that showed each of these stages, the filtering, the imitation, the coaching, every single one added a significant performance boost. It really proves this whole specialized approach works. Right. Enough about how it's built. Let's talk results. How did this thing actually perform in the real world, or at least in a simulated one? The paper says it beats 9 other methods and 10 other LLMs.
It does. And first, let's talk about the state-of-the-art comparison. Light GPT performs just as well or better than the top RL models like Advanced LLMLight. But here's the kicker. Advanced LLMLight usually needs to talk to the traffic lights at neighboring intersections to work well. LLMLight achieves its results using only data from its own intersection. It's just smarter on its own.
And it's not just smarter, it's way, way cheaper. And that's what gets city planners to actually listen.
This is a huge deal. The cost difference is staggering. Even their smallest model, Light GPT Quen 2.5b, which is tiny, performs better than the massive Llama 270b model. And look at the annual cost for a small city, say 100 lights. With Light GPT, you're looking at around $22,000.
$22,000.
If you tried to do the same thing using the GPT-4 API, you'd be paying an estimated $1.6 million a year.
Whoa. Okay, so $22,000 versus $1.6 million. That pretty much settles the why build a specialized model debate right there. But what about when things get really complex? What about scale?
That's maybe the most impressive part. They tested it on a huge road network model in New York City. We're talking 196 intersections. And the RL models, they just fell apart at that scale. They created these huge, long waiting times for some drivers.
Which is a huge fairness issue, right? You can't just have one street flowing perfectly while another's a parking lot.
You can't. And Light GPT, because its reasoning is more human-like, it managed to deliver both the shortest average travel time and the shortest average waiting time. It was efficient and fair. And remember those crazy high traffic scenarios? 4 times the normal volume. The RL models were a disaster. Some were even worse than just a simple basic timer. LLMLight, on the other hand, stayed robust. It just handled it.
And all of this comes back to that key idea of interpretability, that it can actually explain itself. I saw the example in the paper where it identifies the most clogged left turn lane and explains, in plain English, why clearing that lane first is the best bet for everyone.
And they didn't just assume that reasoning was good. They had 15 human experts, traffic cops, experienced drivers, AI researchers look at its decisions. And the feedback was overwhelmingly positive. They confirmed its reasoning was sound and applicable to the real world. That builds trust. Now, as good as this is, the authors are very clear about the limitations, and those limitations really point the way toward what's next for intelligent transportation.
So what's on the immediate to-do list?
First thing is multi-agent cooperation. Right now, each Light GPT is an island. The next step is getting them to talk to each other, to coordinate across a whole city grid for a truly global optimum. Second is multimodality. It's currently working off text. The future is integrating camera feeds, actual visual data, to give it even more context for its decisions.
I can see that. Being able to literally see an ambulance coming or a sudden lane blockage, that would be a game changer for its reasoning.
For sure.